Hi everyone, welcome to another round of Python tutorials. Hope you spend a little time familiarizing yourself with the Python programming language, the syntax, and all the more fundamental stuff we introduced last time. Today, I would like to focus on Pandas. Pandas is a library for data management and data processing. It offers us basically two key classes. One to store tabular data, which is the data frame, same name as in R, and you will see it's quite similar to the R data frame, a bit more powerful, more than a bit maybe. And well, the other class that's offered in this library is essentially one column in a data table. That's called a series in Pandas jargon. You'll see that. And we will basically explore this library in the scope of doing some explanatory data analysis, trying to be a bit more application-oriented in this tutorial. Our use case will be that we got some data and now want to familiarize ourselves with that data, what it's about, what patterns it might exhibit. And so we'll first of all load the data, then use some standard routines to get an idea about the data, calculating descriptives, for example, and we'll do a little bit of data prep, some missing value treatment, some outlier treatment, etc. And in the second half, well, we'll basically run through a couple of nice graphs that we can create easily using, well, Pandas, but also the Python plotting libraries like Matplotlib and Seaborn. And in a nutshell, the stuff that you find in this tutorial should really help you out when you get a new data set to have an idea, to get an idea what it is all about and to play with it. All right, that is it for the introduction. Let's zoom into this tutorial, which obviously you can find on our Gitpad repo to follow along. The first half, I will basically do some coding. I've cleaned that part, I've cutted these parts out of my version of the tutorial. On GitHub, you have the full solution, just to let you know. And in the second half, we'll basically transit into a walkthrough where there is maybe a little bit too much code for me to write that all, but we'll go through it. Anyways, let me zoom in so that you can read that a bit more easily in the video. 200%, that should do the trick. Right. So, introduction to Pandas, some basic data prep, and then some EDA. That's our agenda. And as usual, for start, we'll just load a bunch of library. We have NumPy here. I won't need much NumPy, but a few functions from NumPy occur. Our key thing today, the Pandas library, where the standard acronym would be PD. And then I'm also importing Seaborn and Matplotlib. That's for the graphs that we'll need later on. All right, so let's run that. Here's just some configuration to make sure that the figures are in the size that I want them. Also relevant only for later. Just feel free to ignore it for now. Those of you who've done business analytics know that I'm quite enthusiastic about credit risk and that I'm doing research in the scope of credit risk. So unsurprisingly, since we need some data to introduce Pandas, the data I picked is one from the credit risk space. And specifically, I will use the so-called home equity dataset, or HMEQ, which is publicly available after a little registration wall at www.creditriskanalytics.com. You can get it from there, which would be the preferred approach, but for convenience, you'll also find it on Moodle. And I will assume you somehow got hold of that dataset, the website, or Moodle will do it, and have downloaded it. It's a CSV file, and there are functions available in Pandas that would allow us to load that easily. For instance, I could just basically create a variable. I call it credit. And since I have loaded Pandas earlier on, I can now use PD, the shortcut I was introducing, dot, and then one hit of the top key should bring up a little tooltips. Here we go. And then you'll find sorry, read CSV. There you go. And well, by the way, read Excel here, you'll find that as well. Convenient. You can read JSON files, HTML files, a couple of functions to read various types of data files. We only need the CSV. What's wrong with my typing? I should type it and not rely on the tooltip too much. Read CSV, and well, essentially, I need to tell this function where it can locate my file on my hard drive. So I could give it a variable file, provided I declare that earlier on. That would be all it takes to read a CSV file from disk and store it in a data frame, which I'd call credit. What I have experienced in the past that students sometimes have a little bit some difficulties in doing the housekeeping here, organizing the files, or coping with folder structures and folder paths. And I have to admit that it's not always trivial, or maybe a little bit, well, tricky at first glance. So assuming you're new to Python, you will have stored the data somewhere on your hard drive. And now you need to specify the path. What you could do is you just go to your hard drive and try to find the data there. For instance, I would have it in a folder, Adams, programming Adams data, and then somewhere there's the data file HMEQ. I realize that's very hard to see in the video. I'm just basically, can I zoom in? Not really. Just locating the file on disk, and then I could just copy the full path using Control Copy, and then going back to my notebook, I could paste, just copy paste the path here. HMEQ.csv. Well, supposedly that is not going to work. Indeed, you'll get an error, something goes wrong, and that has to do with different operating systems. I'm on Windows, how they basically structure this path. They use the backslash. Windows uses the backslash to indicate the folder structure. And if I just use this text here with the backslash and everything that's in there together with read CSV, as you see, it basically crashes. What's a good way to handle that? You can also work with relative paths. Relative paths make your life, in my opinion, a little bit easier, especially if you have organized all your Atom stuff, for instance, in one folder. Or you have one folder Atom somewhere on your hard disk, and then there you have a subfolder data, and another subfolder slides, and yet another subfolder exercises, something like that. Actually, I've done something similar. I just saw how the resolution was pretty poor when I brought up my Windows Explorer. So let me show you this structure that I have here using some Python code. There is a library OS for operating system. That's quite useful, and it helps you to interface the operating system. And you can do things like finding out what's the current working directory in my notebook. So where on my disk basically is my notebook currently running. Well, working directory. You know that from R. Don't need to make such a big deal out of it. And here we have a function os.get current working directory. And if I run that, you basically here get the path. And you see how the backslashes are quoted with yet another backslash. And if I now change my path here accordingly, just putting in a backslash bring in a backslash in front of every slash, that would already work out. Then the code would run and I could read my file. But alternatively, now that I basically know what's the current working directory, I could also specify, and that's what I'm going to do, a relative path. What this basically tells me here is that I am currently running this notebook in a folder Adams, exercises, exercise 2. This is basically where I could put the data file and just read it. Afterwards, I could just read it by using the name hmeq.csv. If my data file were stored in my working directory, I could just read it like that. Well, that would be one option you could do. Just copy your data in your working directory. That's fine. I know that the data is not stored in the working directory on my machine, but I do know that where I store my data, that's a folder, data, which is underneath the folder Adams. And currently I'm 2 levels deeper than that, so I could go up by 2 levels, and that's the syntax to do so. The double dot, basically, if occurring in a folder path, the 2 dots say go 1 folder up, and now I go another folder up. So basically from X02 Python machine learning, the first double dot brings me to exercises, the next one brings me to Adams, and I know that there is a folder data, and I'm sorry, in that folder I have stored my file. So that should work on my machine. Wonderful, no error. That means everything worked out. Well, I could also convince myself by just typing the name of the object that I created, credit. Then I already get a nice p-review of my data and a nice table with column headers, values, everything. But this was just the visual proof that the loading of the data has worked out, was successful. I can imagine that you need to play a little bit around with this and might need a little time if you're new to Python programming, or well, maybe programming in general, till you really found your way to load the data. But once you found your way and know how to do it, that will never ever cause you problems again. Okay, so basically I have now my variable credit, and this is where my data is located. And you already saw that once I have loaded my data into a data frame, just keying in the name brings up some nice demo of the data, a preview if you wish. I would get the first 5 rows of the data and all the columns, and then ... and then also the last bunch of rows are shown to me, plus a summary which has close to 6,000 cases and 13 columns. Nice. And just keying in the variable is enough to get that. And we can, as usual, also ask a variable for its data type. And here we have the most important class for today, the Pandas data frame. Let's look through some standard functions that you can invoke on a data frame to basically get some information. One is the function shape. Shape is important. Shape, that's wrong, returns the dimensionality of the data. And very often, you probably remember that from beds, very often you might need to query the number of cases, the rows in your table, or the number of columns. So shape will get you there. By default, you get this result here, which is a tuple, the data type in Python, which basically stores a set of values. We have one for the rows, one for the columns. you can index that tuple just using standard indexing. So shape 0 should give me the number of rows. There we go. And equally, shape 1 will then basically return the number of columns. And should you wonder, shape 2, what will that return? Just an error, because there is no third element in that tuple. So that's shape. That's pretty important. There also is one function, size, which is sometimes a bit confusing, because you might expect to now, well, get the size of the data frame, and you do, but, ooh, wow, that's a large value. And if you think about it, well, not sure you want to think about it, but if you look up in the documentation, size is just the product of rows by columns. It's the total number of elements in your data frame. So don't be fooled by expecting size to give you some information about the number of rows and columns, cases and variables. It doesn't. What you typically want to use is shape. Obtain a high-level overview. That's always good. And you can get that with info. Quite a neat name, isn't it? If we use info, we first of all get the class, data frame, the number of entries, and the index, which by default, because I haven't set an index for my data frame, I could do so manually, setting an index. That's very useful if you have temporal data that you want to index by time. In our case, I haven't done anything about indexing. The index is just a running number from 0 to 1 minus the number of cases. And then we get the columns and their names. We have bad, loan, more due, value, reason, etc. We see how many of them are not null. Null means basically that the value is missing. So by looking at this bunch of numbers here, there are some variables where apparently there are quite a few missing values. Here, for instance, we have close to 6,000 cases, and we have only 4,600 or 4,700, say, which are non-null, and all the rest are missing. And lastly, you get the data type that Pandas has picked upon reading your CSV. For bad and loan, it selected an integer, a float for the other ones. Two variables, reason and job, are stored as objects, and the others are all floats. You can configure that. Upon loading the data, you could specify the data type for each column. It's a bit more programming, and I didn't want to do it today, but especially when you load larger data sets, that's quite useful to ensure that every variable is stored in using an efficient data type. This is not really efficient here, and we will change it later, but you could also change the data types up front by specifying when loading the data that, for instance, you want all your numeric variables stored as a float, but only with precision 32. Float 32 is the data type that is alternative to float 64. It's not as precise in terms of how many digits after the comma are stored, but it's typically enough. We'll do that later. Preview of the first few rows, yet another function that you will use very, very often. Head the first rows, and then you can just look at your data, right? That's so useful. What columns have I got here? What do the values look like? Okay, here, reason, job. These one, if you remember, they had data type object beforehand. Now you see why. These are actually categories. And we have all these nones here. So indeed, there are values missing. Right, so you really get a first impression about the data. Oh, that one looks pretty bizarre. Depth inc, none. That looks not too good. Remember, it was the one where we had only 4,600 or so values that are not null, and all the rest were none. And we already see that here. And where there is a head, there is also a tail. So you just could go tail, and then you have the last rows. And with both of these, you could also say, well, head, give me the first 10. And then you get the first 10, right? 0 to 9. Here we go. So info, head, shape, these are clearly some functions you will want to remember when working with data, and that we will. Right. I left a little description in that notebook. With the previous functions, we already got a little idea about our data frame, I believe, but here's a little dictionary. As I said, that is a credit scoring data set. So we have a binary target, which is bad, where values of 0 and 1 mean that there was a repayment of this credit here, or there was a default event. 1 is a default event, so these customers got credit but didn't pay it back. So bad borrowers. Our target variable, bad. And then all the others are independent variables, the amount of the loan that was initially requested, the amount due on existing mortgages. If you lend some money with the bank, of course, the bank is interested in how much other credit obligations you have to pay back. And this looks specifically at credit applications, credit obligations of the applicant for real estate purchases, for mortgages. The value of the current property. The reason is either debt consolidation or home improvement. So that is a mortgage type of data set. And it's about real estate. Maybe you want to improve your house, do some renovation, or you basically have different credit contracts to pay back your debt and want to just to consolidate these, putting them together, something like that. Job encodes the occupancy of the applicant, years at present job. That's a typical variable that we use in credit risk. If you switch your jobs more often, you are a riskier type of borrower. That's how a bank will perceive you if you switch your job very often. Number of major derogatory reports, number of delinquent credit lines. So that would indicate that you defaulted on a loan before. Also, this is type of derogatory report, so bad credit report, that something went wrong. Number of recent credit inquiries, that's, well, maybe a subtle indicator. If you, well, you know that you need to show your Schufa score when you want to rent an apartment in Berlin. Probably you were asked for that. And once you inquire with Schufa, what's my credit score, what's my Schufa score, that is filed as a credit inquiry. How many times has somebody asked your credit score? And you can guess that if that happens very often, that's maybe a sort of red flag or bad signal. Why is your credit score pulled so often? Do you have so many running contracts, or what's the underlying reason here? This is why the variable comes up here. Number of credit lines, so how many credit products you basically pay back. And debt to income ratio, that's a key variable in credit risk modeling. Debt to income makes total sense, right? How much money do you want to borrow, and what's your income? What's your potential? What's your power to pay back debt? And the ratio of that, you can guess how this is a very important variable. Okay, so that was just a quick overview so that you know a little bit about these variables that are going to show up a lot. And the next Pandas functions I want to quickly introduce is describe. It's also a wonderful function. You have to write nothing more than this bit, the name of your data frame. I call it credit, and then you go describe. And then for almost all of the columns, you get some descriptive information, the count, mean, standard deviation we've got, the minimum, the quantiles, the maximum value. That's useful, right? By default, you get results for all the numeric columns in your data frame. And going back to info, we had two columns, reason and job, which are stored as objects right now. These are categories. And categories, the Pandas function reads CSV, it cannot make sense out of categories. It just leaves them, or it cannot make sense out of text columns. It just leaves them and stores them as object, which is the most general data type there is in Pandas. And now, if you look very carefully, you will notice that describe leaves out these columns object. It sort of by default just looks at the easy bits, where you have nice numeric columns and can compute all the statistics here. The scrolling is a bit difficult on this high zoom factor, but I realize that the resolution in the video is sometimes really painful and that you basically can't see anything if I don't zoom in that much. Right, so no reason here. That's what I'm trying to say. No reason, no job. These variables are filtered, but you could remedy that if you wish. There is a way to force describe to consider all the variables by saying include, and then there are different ways how you can use this parameter include. And as always, it's a good idea when you work with some function. The tab key shows you tooltips that help you locate functions that are available. And by hitting Shift tab, you get the documentation of that function, the signature, in which you see which arguments are available. So you can ask for percentiles, include by default, that's none, exclude, you can include or exclude certain columns apparently. And if you hit the plus sign, you get some more information, the full documentation, which would also at some point touch upon the arguments. Percentiles, list like of numbers, optional, the percentiles to include in the output. So you can't only go for the third quartile, the first quartile, and the median. You could basically specify here which one you want to see. Include all, list like of data types or none. So you can say all, give me all, every column. You can also subset the columns that you want to describe by data type. We will see operations that depend on the data type very soon. So I'll leave it by now, just go for include all. And then we would also get some information about reason and job that was previously not part of the output. And well, you see why it was not part of the output by default. Since these variables are objects, there is no way to calculate something like a mean or a quantile. It doesn't make sense. And instead, you can calculate things like the number of unique values or the frequencies. And this is basically what you get here. And these unique top and frequencies, that doesn't really make any sense for the numeric variables. And this is why you have introduced all these nonce value here. So by forcing all the columns into my result, the result gets a bit harder to read because now I'm having some rows that only apply to the two variables, reason and job, and all the other rows only apply to the numeric variables. That's why this is not the default behavior. Okay. And by just going through these examples, you can guess that there is quite a bit for us to do in order to prepare our data for analysis. We should really take care about the missing values. And well, since we are looking at this nice list of descriptives, consider loan, the variable loan. So that is the amount of money that the borrower asked for. And you see that on average, that's a little less than $20,000 with a standard deviation of $11,000. Okay. Smallest one, 1,100. Mean, 18,000. So the median is 16, reasonably close to the mean. 23 here is already our third quartile. Okay. And the maximum is close to 90,000. So just looking at these numbers, or that one here as well, that's mort due, so other mortgages, and what's the amount to pay back there. You get the mean, and you do see here the maximum. By just looking at the maximum, you get some signals that there are outliers in the data, or that these variables have a distribution with rather long tails. And probably you want to do something about that. And yeah, we will. So let's do some basic data prep using Pandas. First of all, I want to do something about these data types. On the one hand, some data types are just wasteful. That, for instance, is a Boolean. That's a variable that stores 0 or 1. So you need 1 bit to encode that, to store that. And currently it's stored using 64-bit integer. That's wasteful. And also reason and job, these are categories. And you will remember from your R lessons that there are specific data types for categories. In R, it's a factor. In Python, there is something equivalent to a factor. But we need to tell our data frame that this is a category and that job also is a category. And I also want to downcast the numeric variable, but mainly for illustration. So remember that number here. Currently, our data in memory consumes a little more than half a megabyte, 605 kilobytes. That's no problem. Yet, by the way this is stored by default, it's wasteful. Let's do something about it. And well, here, this part of the notebook is to illustrate some functionality that you might use or might want to use rather often when working with a new data set. First of all, that's the first occasion in which you see indexing. That's one way of indexing a data frame here. I just give the name of a column, and basically that gives me access to this column, all the cases in that column, so the full column. And just because I was using the term before, let's check credit reason. Let's check the type of that. This is the other prominent, important class in the whole Pandas library, the series. So one column in the data frame, and you see one way to extract this single column, this series of the data frame with this index. We'll see some other ways to do indexing very soon. So I'm pulling out this column, and then I convert it by using the function asType. That's an important function, asType. And the argument of that function is basically the data type that I want to translate to or convert to. I take my column reason, and then I convert that into a new data type. And the data type I've picked is category. That's the data type to use. That's what R calls factor. And the result will be the data stored in the column reason converted into the data type categorical or category. And here I need to basically reassign that result to the original column reason. So basically I overwrite what's stored in reason with what is stored in reason but converted to the data type category. And I do the same for job. Maybe we can just run that. It's maybe a bit trivial, but anyway, let me do it like that. So basically for reason, I do everything correctly, but for job, I forget to do the reassignment. That's the idea. And here I can use this line to remind us all about the current data types used in my data frame. Currently, both are stored as object. And now let's run this code and afterwards call the info again. And we see how only reason is now translated into the category and the other one has remained as object. Just the proof, if you wish, that that returns the converted data, but it would not change automatically the data frame. And if I want my data frame to change, then I need to manually or explicitly reassign it like that. And afterwards, yeah, now I have both my variables stored as a category. And actually, that alone was enough to reduce my memory consumption a little bit. And if you think about it, that's more than a little bit. From 605 kilobyte, I cook it down by 80 kilobytes just by changing this data type. That is to showcase how the data type object is wasteful. So you want to avoid using their data type. Okay. Here we go. Basically the same for my target variable as type Boolean. Nothing new here. Loan is stored as an integer right now. And although all the numbers are integer numbers, for convenience, I convert it to a float. Why is that convenient for me? It's convenient because then all my numeric variables are stored as the data type float. This is why it's convenient. And here, by the way, I'm using the NumPy library, which offers all these data types. And the next one is more important. Here, let me split the, let me do that bit. It's not interesting. That's more important. Here we use a function select dtypes. And again, that's one function you want to remember. If you have a data frame, it's typical that the variables in the data frame are heterogeneous, that you will have some numbers and some categories. And very often you want to do something with the numbers. Maybe you want to replace missing values using mean replacement. That's fine for numeric variables, makes no sense for categories. Or you want to scale your data, fine, you scale your numeric variables. Very often you need a way to say, give me all the numeric variables from the data frame. Or give me all the categories. Maybe you want to do weight of evidence coding. That applies or is feasible for all the categories. So very often you will want to filter your data frame based on the data type, where the data type is a kind of proxy, if you wish, for numeric variables, continuous ones, and categorical ones on the other hand. And this is why this function select data types is very useful, because it allows you just that. Saying credit.select data types, give me all the columns of a certain data type, include, there's also an argument exclude, so I can do it one way or the other. Here I'm using include. I include all the columns of data type npfloat64. This also shows you how it was convenient before to convert the data type of loan to this data type npfloat64, because now I can access all the numeric variables in my data frame in this way. That bit of code, let me show you that, because maybe a little bit important. If I run that bit of code here, it's very important in Python generally, but also in Python, to be aware of what data do I get back when running a function. What's the result of a function? And if I use type in order to find out what's the result of that function, I could also look into the help. But very often it's easier to just run it and look for the type. Okay, so that function gives me a data frame. Meaning that, I would now have a different data frame. If I continue working with that, we don't need that anymore. And here I basically use the method columns, which gives me an index of all the columns in my data frame. And that's what I'm storing. And I'm using this index of a set of columns, a subset of a column. I'm using that here to index my data frame in a reassignment. So I'm overriding a bunch of columns, all the numeric columns. I'm overriding them. What's the value with which I override that? With a new data frame, if you wish, where exactly these columns are converted to float 32, which is a data type that is not as precise, but also needs less memory. Let's run that bit. Okay, now I see that, well, I have one Boolean, two categorical variables, and the rest are numeric variables stored as a float 32 with some precision. And look at that. We had 65 before, and now we have 250 kilobytes. And this is tiny data, I know. But if I give you a data frame that has a few hundred megabytes, or once we move on to text data, which is quite big, then you will see how easily you can basically exhaust your computers. And this is when considerations like this one here will become really important. Actually, I could quickly check. It's probably very hard for you to see. You might not see anything, but I want to check that out. Okay, I'm doing a video, so currently all my memory is consumed by OBS Studio, which is the software I'm using to do the videos. Where's my Firefox here? So even with this tiny data frame, my Firefox already uses 500 megabytes, close to 500 megabytes. And this is really tiny data. So that's just to show my point. It's maybe a little bit mechanical what we're doing here, but on the one hand, you'll get to see some important Pandas function, and on the other hand, this considerations, how do I store my data? I tell you, it's really important. Okay, one more bit. We have used the function select data types, and it's a convenient function, and I was telling you that you will probably use it a lot, and feel free to do so. Actually, it is a little inefficient. With many data sets, you won't notice that. And this data set is one where you won't notice the inefficiency of select data types. But you could guess from my previous demo how this returns a data frame that even if I just want an index to the columns, by using select data types, some copying of the data goes on in memory. Although I just want an index of the columns, I don't really want the data. And when you work with large data sets, or when you have an older computer which has not so much memory, you might need to program with keeping an eye on efficiency. And I wanted to show you some way to do that much more efficiently, which is list comprehension. That's used a lot in Python, but it's a part of the language that can really give you a hard time if you are new to Python. It's something quite specific. I haven't seen that much in other programming languages, and also the syntax is quite bizarre. So instead of getting an index to all the numeric columns using select data types and creating a data frame on the way, I could do the following. I have this square bracket here, which is for lists. And now I'm going x for x in, I'm sorry, talking too much, credit.columns. Credit.columns. That's a list of all the columns, basically doing a for loop over that, so enumerating all the columns. If, now it gets bizarre, if credit, since that is an index over the columns, I can use it for indexing, credit x dot dtype in, well, I know which data type I'm looking at. I want the numeric ones, so I could reuse my variable filter. Well, let me copy that here so that the code is easier to read for you. I just create a list with all the data types that interests me. And then I say in filter, and that's it. For x in credit columns, if credit x dot dtype in filter. And yeah, as I said, that looks pretty horrible from a clarity point of view. That's called list comprehension. So you basically press a for loops and conditions in one line of code, which is good on the one hand, but you really need to get used to that. There are two things here, two things to note. First of all, this list comprehension thing, I wanted to introduce it because if you look up code online, it's used a lot. So you have to make your peace with that. And on the other hand, this contract here, it goes directly through the columns, checks the data type of the columns, it avoids copy pasting, unlike select data types, and therefore it's more efficient. And well, I was basically tracing the time before. I could also do that here. Start. It's not a very accurate way to trace how long your computations take. All right, so let's say this has taken me, remember formatting, format, well, I could actually format that as a nice number, and then, okay, I need a variable, t2 equals end minus start, and then we have t2, and, oh yeah, these are functions, so I need to do it that way. There we go. And what was it that we had before? That doesn't make sense. If you, well, seconds, and if you have something like 0.00 seconds, that sort of signals, hey, come on, time doesn't matter, which is true. But actually, if you look at that, The second way was so much faster. That's a factor of 10 faster. And although we didn't notice it because our data is so tiny, you can imagine that a factor of 10 will make a lot of a difference if you work with bigger data sets. So keep that in mind. I'm stressing that, and you really might wonder why I'm spending so much time with it, but this select data types, again, it's popular, it's widely used, and you will need it very often to just subset your data and extract all the numeric or all the categorical variables. That's a very common use case. Okay, but if you have a big data set and you use select data types often, the select d types function, that guy here, you use that very often, you will experience how your code is slow. It's going to get pretty slow. And well, for most of us, we don't really have enormous, powerful server computers with tons of memory available and well, powerful GPUs, etc., etc. Most of us normal people, we don't have that. And in a way, it's good because this scarcity of very powerful compute resources teaches us to be a bit careful with how we do programming. And although this function isn't so well used, note that using list comprehension, you can do it much more efficiently. This use case, getting an index to all the numeric or all the categorical columns in your data. And well, because list comprehension is kind of hard to understand and appreciate at first glance. I left a link to some nice blog posts. Look at that picture here. That basically explains to you list comprehension in one picture. And I think this is really beautiful way to visualize the thing, how this statement that you squeeze into the square brackets here um, essentially is one for loop plus a condition plus some operations, and you can squeeze all that in one loop. So if you're really serious with Python, list comprehension is one thing to look for. And this post here by Peril Pendy, it's a good read. So have a look at that. I think it's a 7-minute read or so um, with the time. Okay, so by now we've basically manipulated the data storage in our data frame to enhance efficiency. And you've seen how our memory consumption reduced. And now, very important use case, of course, is indexing. And you have already seen indexing. You can do things like credit, and then you give it a column name. And as a result, you will get access to this Pandas data series storing the corresponding columns. And if you just output it, it will look like that. Basically a preview and some meta information. How many observations, what's the data type? That's one way. There is another way, which is equivalent. All the columns from read CSV also have by default an accessor. What do I mean by that? You can type .bat, .column name, and the result is the same. You also get access to this Pandas data series. And probably you could also prove, I'm not sure whether the equal operator works on series. Yeah, okay. It does, but that's just to show that you really have the same. Well, I would need to show you that the memory address is the same. That goes too far. Anyways, so these are two very common ways to access a column. One popular use case. You can also index Pandas data frame in a way that's maybe more familiar. Right, so R* indexing, you just go credit and then you need log. And that is localized. So localize allows you to index in an R-like manner. We could do 0 to 5, for instance, and then we could index a single column like that. Here we go. Or you could also give it a list of columns, loan and what else? CLH, we have got client H. Well, that will do the trick. And oops, sorry about that. Yeah, here we go. So we have a numeric index for the rows, and for the columns, we still give it a string-based index. We use the column headers, that's what I'm saying. One of them, or you create a list of column headers. In R, we use the function C for that in order to concatenate a bunch of column headers. And here we just use the square brackets to create this list of column headers, and that allows us to index in an R-like manner our data frame. And by now, you have always indexed columns with their name. That's good, but sometimes you will need to index columns with their number. So maybe you want to have a column 3 to 5 or 3 to 6. And that is, of course, also possible. But you need yet another function. To access a column by index, you need the function ilog, credit dot, that's like index localize. And then we could again say, give me the first 5 maybe observations, and give me the first column, which I know is bad. It's not bad, but the column is bad. And here again, I could also create a list saying that I want the first and the second and the third column. And then you basically have your data frame. There you go. ilog and log. That is R-style indexing. It's not possible to do all the, or to have all the possibilities that R offers you for indexing data frames in one function. You need to know log and ilog, but I think it's not too difficult. And very often you'll be fine with just using this column indexing anyhow. What else have we done in R? A lot of logical indexing we've done in R, and that works as well. Here's an example. You can use the function query. My query is that the value for the number of credit inquiries, and inc, that's the variable, and that number I want to be larger than 10. That's simple comparison. I can give that comparison to credit.query, and that will give me a data frame having all the entries where my condition is true. Let's look at it. So again, a bit inconvenient with this high zoom factor. Anyways, you'll see that you have the result. You see that it is a data frame. Can convince yourself using type if you don't believe me. Type temp. So there we go. Query is a good way to extract a more complex subset from your data frame, something that you can't really do with indexing alone. Query will help you to achieve that. But again, being more R-style, there is also a way to use a local index together with log. And I'm illustrating that here using the log function again. And then with log, I'm basically subsetting the rows with a logical expression, column bad equal to 1. So I pull out all the bad applicants from my data frame. And for these applicants, I look at the loan, the job, and the YOJ, that was years at current address, I believe. So that's logical indexing. I think best for you is to remember everything you did in R is possible in Python as well. It's maybe a little more complicated. in that you need to remember these different ways of indexing. Clearly, you'll get used to it, but a little bit of practice is needed here. So just remember everything is possible, but I might have to use a certain function. And remember that this tutorial number 2 is where to find the most common, I believe, ways to index a data frame. Good, let's move on. That was core data handling. We have a lot of missing values in our data frame. Let's replace these and introduce some more Python functionality on the way. First, how do I check for missing values? And to have downward compatibility, there are two functions that do exactly the same thing, which are isNow and isNA. And you can apply that to a data frame, or the data frame offers this method, isNA or isNow, and that basically gives you a matrix of all booleans of the same size of your data frame. Let me show you. And then this is like a mask that you can use for indexing, and it will highlight those cells where a value is missing. Okay, that's nice. It has the same dimensionality of your data frame, obviously, because it's a mask. But while that is nice, you will normally not be able to make so much use of that directly because you can't replace all the missing values across all the columns in one go. Typically, you can't do that, and so you will rather have to process your data frame column by column when you replace missing values, and that is what we will do next. One use case, however, since you have this matrix here, you can basically just sum over it, and that will tell you the number of missing values per column. And also you can also sum over that, and then you have the total of missing values, which is a lot, right? 5,271, that's a lot of missing values we need to get rid of. Okay, now we have the notebook that you see, counting missing values. And here, if you do that with the other function isNow, nothing changes. In my notebook, I was using isNow more often, so I should stick to that one. Let me show you a nice way to get a visual expression of all these missing values and how they distribute across the columns. I'm using the Seaborn library here, and that offers a nice way to do heat maps easily. And I can just give it this isNow, this matrix with all the cells being null or not, so having a missing value or not having a missing value. And if I create a heat map out of that, or this information, if you create a plot in this way, you basically get a handler to that plot in return. So the function heatmap returns something. One easy way to get rid of this message here, which just says that, hey, heatmap is returning you an object. You don't assign that object to anything. Quick way to get rid of that if you don't care is using the semicolon. And then we have this heat map here. Because our values are all true or false, 0, 1, it's only black and white. And since it's black and white, we could also get rid of the color bar. And then here is our heat map. And let me zoom out a little bit. So we have for all of our variables, basically, and all the rows, we see where the missings are. And well, I like that way of looking at the data. It would show me, first of all, that bad and lone, there are no missings here, which is good. And it also reinforces that this variable debt to income is really prone to a lot of missing. You can speculate that the corresponding customers, for some reason, didn't give their income. The debt should be known to the bank anyways. And yeah, this helps you to know where are my variables that are particularly prone, have a lot of missings, and where are variables that only have a few missings. That one here maybe. Client age, there are some missings, but it's not that many, right? So in a variable like that one, where we have a few missing values, but it doesn't really look dramatically, you want to do something, maybe you are happy with doing a quick fix. And that pattern here, where you have a variable you believe to be highly indicative, debt to income ratio. For a banker, it's a no-brainer that is a very powerful variable in a risk model. And if you then have so many missing values, so that's something where you want to spend your time on. Here you might want to consider building a mini model to do the imputation of the missings. We won't do that, but this is why I like this plot. It's quite telling. Well, still, I'll be a bit rough with treating missing values. I just have the categories where I gonna put in the mode as a replacement. They're not, oh yeah, here we have reason and job. Well, it's hard to tell. Maybe job is a little more prone to missings. We could easily count the number of missings, right? We did that above actually. And reason is maybe less affected. Let's illustrate two ways of proceeding. For reason, let's say reason is less affected by missing value. We don't have that many. It's a categorical variable after all. Let's just introduce a new category, missing. Well, let me create, since now I'm playing with my data, let me make a copy. That's often useful if you can afford the memory. Let me make a copy. So I now df really points to a new fresh data frame with the same entries but stored elsewhere in memory. And any change I would make to df, it's not going to affect my original data frame credit anymore because I copied it. Reason, here we go. Yeah. We have two factor levels or two category levels, debtcon and home imp. And we know that there are a few missing values. You already see some here, none. So I want to show you how you can introduce a new category level and then basically assign every missing value to that level. That is one way of proceeding. Let's say later on you believe you will work with tree-based algorithms that are happy with categorical data. Then it's actually fine to just leave missing as missing, but make these a category level would be a good idea. And you might be tempted to try that like this. Access the column, access the null values or the missings in that column. So now I have this index here and just assign them a new level is missing. That's conceptually that's perfect, that's right, that's the way to do it, but it will fail. And the reason it fails is that since we made reason a categorical variable, Python is a little bit protective here and wants to ensure that everything is sound, and it doesn't know that level. It doesn't know the level is missing. And this is why I'm getting this error. So before I can just say, well, all the missing values that I see in that variable reason, I just assign them to a new category. I have to introduce that category. And to that end, we can basically reason. We access that variable, and then since it's a categorical variable, there is a way to use this .cat, which now provides a bunch of functionality to deal with categories, one of which is now I can add a new category, add categories, and it asks me for a list of new levels. Although I only want one new level, I need to put it in as a list. Here the documentation is not really that helpful, but it would say me that the first argument, new categories, is a category or list-like of categories. So anyways, so here we go. And that also allows me to make this change to my variable because I want to change it. I want to change my data frame. Often, not always, but often it's possible to do that in place because this function knows an argument in place. In place equal to true means I don't want the result, which would be the series with the new level is missing. I rather want to rechange my data frame. So this change should be implemented in place, in memory, where my data frame is located. And with that bit, everything should work out. And it does, and now you can also see this new level is missing. Remember, I'm always trying to strike a balance between doing something that is vaguely useful and showing you some standard routines in Python and Pandas. Well, here I think that's quite okay. That would be a legitimate way to handle missing values in a categorical variable. Just leave them as missings and make missing a new category level. And then you also learn some way of doing that in Python. An easier way to handle missing values in a category would be to just replace them with the mode. And I believe that it's less suitable for reason because there are only two levels, depth consolidation and home improvement. And if I do mode replacement here, then one of the two levels will get inflated very much because there are a lot of missing values. For job, it's not that much. There we have, let me show you, reason.job. That's nonsense. Here we go. We have manager, office, other, prof X, sales, self. We have a bunch of categories. Let me show you another useful function, count value. Is it value or values? Count value? Oh, that's nonsense. Neither of them. Yeah, sorry, my fault, my bad. Value counts. That's what I wanted to show you. Value counts, super useful, especially for categories. Tells you how many entries have we got for each of the category levels. And that reveals that other is the mode of that variable, right? It's the most frequent category. And, well, I would suggest that mode replacement here is a possible way forward. So let's do mode replacement. Finding out the mode is also easy. You just use the function mode. That's nice. Pandas has a lot of statistical functions readily available for us, and we can apply them to series, i.e. individual columns in data frame. Mode. That's the result, though. It looks a bit detailed. If I just want this value others, but I can index that. So if I index that and get the first element out of this object here, I have the category level, other, and then I can just do what I did before. A bit lazy here, so let me copy paste that. we're filtering out all the missings using isNull or isNA, but for job. And all of these, we just assign a new category level, which is the mode. Well, we don't see any output here, but we could get some if we just use value counts once again. Well, I did not store the previous output, but had I stored it, well, actually, okay, so now we have 2,667, and that is why I made a copy of my data. I can now get back to the original data, and there yeah, should be less variable, less occurrences of the category level others, right? And you see that it's 2,388, whereas in my cleaned data frame, we have roughly 300 more. So that did its job. Great. So we got rid of missing values, or at least we dealt with them in the two categorical variables. Here is the function to calculate the number of missings once again, or well, slightly different versions of that. I'm using isNull to check in reason whether there are any missing values. And you remember that this is giving you this big matrix of the size of your data frame. And you can use the function any to check if there any true value in the list on which you, or in the matrix on which you apply any. And the same I do for job, and that helps me to basically verify that there are no missing values anymore in these two. And next we move on to the numeric variables. We also have a bunch of numeric variables, and here is select D types again. I was saying list comprehension is more efficient, but since the data is tiny, I didn't bother. So I write my for loop explicitly. For and if you ever, well, whenever you see something like that, for and then if, remember, well, if resources are scarce or if that is an operation that is costly, don't implement it like that. Use list comprehension. Anyway, so what's going on here? Well, very simple code. We select all the columns that are of data type float 32, and I know that this basically encompasses all the numeric variables in my data frame because this is how I set up my data frame. So I'm looping over these columns. Note this columns here. Up to here, the return type, the result from this highlighted code is a data frame. And by using dot columns, I reduce that to an index of the columns in the data frame. So this is a way, this here is essentially an index. Let me zoom in again. I was zooming out when showing you this black and white Seaborn plot, but I had a zoom factor of 150 before, so I trust that the videos will be okay. But I'll raise that to 200 again, just to be on the safe side. Okay, so we are looping, essentially we are looping over all the columns in our data frame. We check whether there is any missing value in the column, df index by column that accesses me the current column. Is there any null value? And if yes, I calculate the median of that column, and that's mainly to show you a different way. I could, as before, so before, if I reproduce what I did for the categories, I would write df call is equal to df call well, yeah, this is why I did it differently. I would need to index the data frame column, and now I would need to index that again using this index coming from is NA or is null. And that is a bit tricky. Because of that, I did another way. I did it differently using the function fill NA. That's a nice one. I'm just filling with that function all the null values in that current Pandas series, in my current variable, using, well, m, that's just a temporary variable that stores the medium for that column in place equal to true as before. So that's easier than handling these double indexing that I would need to index the column on the one hand side and at the same time which entries in that column are 0. All right. I'm sure there are other ways of doing that, but that clearly works and is one way to do it. And then are there, after going through this bit, are there any null values left in my whole data frame? Summing over the column, summing over that sum, value 0, so no missings anymore. We dealt with the missing values, got rid of them. Very good. Done with that. We can now move on with some EDA. And again, we will distinguish between categorical and numeric variables, typically. For the categories, well, what can we do with category? We already introduced some functions like count values, which is useful. You might also want to do a little plot, a bar plot showing you the frequency for the categories. That's something that I'm illustrating here. Let me run that code. Right. Well, is there anything to note? I'm using Seaborn again, SNS for Seaborn. Using the count plot functions, I tell it which column I want to count, which data to use. Oh, actually, I should use my cleaned version here, data frame, instead of credit, which is the original data. Minor issue. I'll make sure I will update our GitHub repo to make sure that it's proper there as well. I'll do that later on after uploading this video. Okay. Yeah, Seaborn offers this count plot, and then I get this nice bar plot of the good and the bad, and I see how many we've got. So we get the frequency, and we can also have that for reason, and we have that for job. All our three variables that are not of data type float. This is how I did that. So that's one way of doing it. For the numeric variables, it's probably a good idea to look at the histograms. And the box plots, well, probably most common plots in explanatory data analysis. Pandas supports histogram natively, so just look at that bit of code here. Say you want to create a histogram of a column in your data frame, or multiple ones. You just select the columns as before, select D types. By now, you should know that well. And then you use hist. You can specify a bin size if you wish. And that bit of code creates you a nice plot matrix with histograms for a bunch of variables. That is really useful. The layout is also quite sensible here, and I really didn't need it to do anything of that. Great. So that I like. I hope you like that too. And if we look at this histogram, we will recognize that several variables exhibit indeed this long tail that we also noticed when looking at the descriptives and the maximum value per variable. You have these little bumps right here. Value is one where there really seems to be a noticeable outlier right here. Sorry, that was lone. This is value. So outliers are our next topic in the scope of data prep. And well, to double check, Boxplot would be good to apply. The Boxplot will highlight outliers according to rules of thumb. I'm showing you a quick and dirty way to do the Boxplot. That's super neat. You just use your data frame and there is a function Boxplot, and that is almost it. Just that this function again needs to know which variables you want to plot. And so I give it a list of variables. There's a little bit of complying with the input data type of function arguments. This is why I wrap that up in a list here, because Boxplot, like the multiple columns to come in the form of a list, not an index or something. Well, if you look at some code and wonder why is he doing it like that, why not simply using select D types again? Well, first, there are typically more than one way of solving a problem or to do a task. And second, that might be because certain functions like Boxplot have arguments and expect the values for these arguments in a certain data type. I want to make sure that that works out. So here is our Boxplot for all the variables. That's very nice on one hand, because it's just one line of code. On the other hand, since the numeric range of our variables differs a lot, all these Boxplots here are basically, well, useless. Since lone, more due, and value, they dominate the whole plot just because their value ranges are much larger than for the other variables. And here is the code that you want to use, being a bit more considerate and creating individual box plots per variable. I'm using ilog. You know ilog. The reason I use ilog here is that I manually do this matrix of plots. I have 10 variables here, and I want to plot these in 2 rows. And therefore, I'm indexing the columns. I'm using on my data frame, I'm using the function plot, boxplot, hist. These are wrapper functions to do popular plots quickly, but I can also use the function plot and apply that to my data frame, which is a lower level function, but tell it the kind of plots I want. So box with subplots. Let me run that, takes a little while, and then that's more useful. You have individual box plots for all the variables. And well, you know how to read a box plot, and it confirms just that there are outliers in many of these variables. Note, however, number of delinquent credit lines. That one here. Also note this one here. These bad reports, the number of bad reports essentially. 0 is the median, and everything above that is an outlier. That's not really, well, this box plot tells me that that variable is different. And basically has most of the entries equal to 0 and a few non-zero. Do we also see that in the distribution? We probably do. Let's look at it here. And, oh yeah, here, sorry. So we have delinquent and derogatory reports where we have this peak at 0 and a rather few non-zero entries, even more so here in derog, but similar pattern in delinquent. So for these variables, if we were serious about the data set, we would probably consider creating a dummy variable, is 0 or is greater than 0. That would be a way to deal with that variable here, and maybe something similar for delinquent, or we could regroup that and maybe make 3 categories out of that: 0, 1, greater than 1, something like that would be suitable. I won't go there because the Python code is not too interesting, I believe, but that would be the way to proceed here with these. And for the others, we will just truncate outliers. And I've prepared a little function. That's a bit too much to write it down live. That implements outlier truncation based on the interquartile range, based on the Tukey rule, which is a quite good way, I believe, to deal with outliers. And also I want to showcase some nice custom functions. So remember the def for introducing a custom function. I call that outlier truncation. I have 2 inputs, x, which is the single Pandas theory or variable I want to process, and the factor, which by default is 1.5. You might remember from your stats lectures that there are mild and extreme outliers, and that this 1.5 is a common threshold. A variable that's 1.5 times the interquartile range above the 3rd quartile or below the 1st quartile may be considered a mild upper or lower outlier. So I introduced that argument, giving it a value of 1.5, but allowing the user who consumes that function to change that. And then, well, we calculate the interquartile range. And for Pandas data series, as I said, many statistical functions are readily available for us, including quantile. So 3rd quantile and 1st quantile. And the difference between is the interquartile range. Then using the argument factor, I can compute the threshold of what I now consider an upper and lower outlier. And then I use logical indexing to replace all the entries where the value is higher than upper or lower than lower with these thresholds. That's outlier truncation, and return the results. That's my function. And then to make use of that, I would again create me an index of all the variables I want to process. And well, just for fun, I do that using list comprehension, which might be an overkill. But indeed, just using data frame select d types would not be enough, because I want to make sure that I do not use this outlier truncation with all the numeric variables, because the boxplot has shown us that there are these 2 variables, deroc and delinquency, the number of previous delinquencies, where the distribution is such that it's 0 inflated. And if I apply outlier truncation to these variables, all my results will be 0. You can try that out if you don't trust me. So I definitely want to not apply outlier truncation on these 2. And therefore, just using select d types would not work here. And well, anyways, I get my list of columns that I want to process using this list comprehension here. And then that's another nice one. Using this index, I go into my data frame, and then I use apply. That also should ring a bell. Apply is an important function in R, and Pandas allows us something similar. We can apply some function, and I'm using my own one, to a bunch of columns at once. Let me run that. And now I should note that if I look at my maximum values in the numeric variables that they have come down a lot. No more 80,000 somethings here. That has killed all the outliers. Maybe I was a bit aggressive with the threshold 1.5 times the interquartile range. That might impede later modeling. I've used it for demonstration. You can be, well, you can allow larger values, obviously, and with this code, you can easily change that also and decide for yourself which values you consider an outlier, and you've seen how you can then get rid of them. Let me rerun the previous code with the boxplots, because now our distributions should look more appealing. And there we go. Yeah, so now, because I was a bit aggressive with my outlier truncation, we have no outliers anymore, and see these max values here. DROC, I didn't change. Delinquent, I didn't change either, but for the others, the distribution looks, well, different. Whether this is better or not, we need to run some models to find that out, but we won't do that today. Right. Okay. Now in the reminder, I don't want to write any code myself. Let me switch to the ready-made notebook. The point in the reminder is mainly to just introduce some common plots. And since I'm already keeping you busy for quite a while and took a lot of your time, I will be a bit quicker when going through that part. You essentially have examples how to create graphs that you typically use in the scope of explanatory data analysis. The heat map we had before. Now I'm using the heat map to create a correlation matrix. My data frame supports Pearson correlation. Well, probably also other correlations. I didn't check that. Pairwise correlations of columns. We also have rank correlation in the form of Kendall and Spearman. And that gives me a matrix of all the pairwise correlations. And then I can create a nice plot out of that using the heat map function of the Seaborn library. And that would help me to note whether certain variables are highly correlated with one another. Here, for instance, that's my target, bad. And this guy here is delinquent. That makes sense. Number of previous delinquencies. If you defaulted on a loan before, quite likely you're a bad risk for the bank. So it makes sense that this variable shows a high correlation with the target. What else is strongly correlated to the target? Anything? That's all pretty small values here. A 26 I got. That's about it. So no super powerful variable immediately discernible. That's the other one here, DROC. You know that variable by now. So the other one, which we didn't prepare. So this correlation matrix further supports the view that you should try to prepare these variables in a better way to increase the predictive power of any model that you want to build for that data set. You could also just carve out the strong correlations. In that example here, I am enforcing a threshold. And plot only those pairwise correlations that exceed my threshold. And then you see again, for the target, it's only one that's above my threshold of 0.3, but I have a bunch of others that are strongly correlated. This here, for instance, value and mod due, mortgages and the value of some real estate, so that, well, if you have some background in the credit business, that also makes a lot of sense. Essentially, it says that if you have a valuable house, an expensive house, you probably also have a big mortgage, which makes sense. What else? Some more in the range of 30. But the point really is, so these type of heat maps are often useful. One use case is looking for pairwise correlation, and this can inform feature selection. We also have a bunch of categories. What to do with these? Well, bar plots are a way to look at categories. And when you count the number of entries in a certain category level, for reason, for instance, we have debt consolidation and home improvement. And we also introduced a new level, missing. You can count the number per level, and then it's often useful to not only count the number of entries per level, but to stratify that across your target, especially classification. And that's what I'm illustrating here using the group by function, yet another useful Pandas function that allows you to group your data. That's essentially the group by that you might know, you should know from SQL. Select from where group by. You can also do that in Pandas using group by. And then combined, well, maybe maybe that was a bit quick. I have my data frame. And let's say you want to do a grouping by your target, which has two levels. And let's say you want to group the variable loan. So that would be select loan, comma, oh, well, and let me continue first, mean. Data frame object has no attribute. No, there is no group by. That is true. That's of course my bad. What's wrong with me? Group by. Here we go. So this group by would, for instance, allow me to calculate the mean loan value for the good and the bad borrowers. And this would be in SQL, select bad, average, AVG, loan from table, group by bad. That's the SQL equivalent to that. And that's useful to do grouping. In fact, you can do that in one go for your entire data frame, or more specifically, the numeric variables in the data frame, and then calculate mean values or other aggregates. But the mean probably is the most interesting one. And that group by is also useful. You see that you need a little bit of more code to get that to work. I don't want to go into too much detail here. That's also useful with grouping to create a stacked bar plot where you then have, for example, the variable job, and you count for all the levels in the category job, the number of goods and bads. That's a nice type of analysis. And you can do the same for reason, obviously. The thing is that it gives you an intuition where how the good and bad distribute across your category levels. Just that it's maybe a little hard to interpret the absolute counts. So I'm providing you here the same example, just normalizing the counts. You find that also in the notebook. And there's this bit here where, oops, sorry, no, that's the crosstab. Anyways, I think well, in this solution, you have this graph twice, once with the absolute counts and once with the frequencies. And the frequencies are a bit easier to work with, I believe, when you have when you clearly see the fraction of bad payers per category level. Right. Other functionality that is often needed for categorical data would be the cross table. Pandas supports the function crosstab to do that, and you can basically run that function and it will do the crosstab with counts. And here again, you might want to normalize these counts to interpret the relative frequency. That's often easier. How the goods and bads, well, spread over the category levels. And when you look for code at Stack Overflow and other platforms, this version here is still widely around. You find that on many websites where you do crosstab and then normalize the counts manually using a lambda function, an anonymous function in R. It's called a lambda function in Python. You write a little mini function here that's basically used in the scope of this apply. So you apply it to every column that you specify earlier on. And it will give us a normalized counts. Note that at some point they improve the crosstab function, and this lambda function is not really needed if you want to have the counts normalized. There is an argument now available in the crosstab functions, and I'm illustrating that down here. You could just say normalize that by index means by row here essentially, and that's obviously a lot easier to get the crosstab with normalization so that we clearly see the relative frequencies and how they split. And here, for example, we would basically see, if we're also trying to make a little bit of sense out of the number, that the goods and the bads, it's pretty much 80-20 across all the three category levels. Right, so there's not much heterogeneity here going on. And so if we were translating that category using weights of evidence or something like wise, well, basically, this consideration informs us that reason probably is not a powerful variable. And here was the normalized plot that I promised you earlier on, where you have the stacked bar plot just with normalized counts or with relative frequencies. And then you can easier interpret, I believe, how the good and the bad spread across these categories. And which category is most indicative here for job, for instance. Okay, if you work in sales, apparently that's a bad signal. You're more likely to be a bad payer than if you work elsewhere. Self-employed apparently also is a signal for bad debt repaying behavior. And that we saw earlier on for the reason why somebody applied for some money. Was it debt consolidation or home improvement? Not much different, really. We haven't looked at that, but probably I haven't emphasized that, but this is about the prior probability of bad and good in the data. And this is why the variable is not very important. Okay, well, some more plots, and maybe you remember that from my bads lecture on EDA, I was showing you some graphs of nice, fancy plots to analyze variables and their distribution, violin plot, for instance. So I took the opportunity to incorporate all these plots into this tutorial. And I think, well, maybe the main point here is to create some wow effects. But for you, to show you how easy it is to do these plots. Seaborn, this library, violin plots. It's a walk in the park with Seaborn. You specify a bunch of arguments, which variable, which x and which y variable in a violin plot. I'm basically combining a categorical variable and a numeric variable, or more than one. Here, for instance, I'm using my target bad, and I'm using the numeric variable alone, and I'm plotting the distribution for my categorical variable reason. So earlier on, I was saying, well, just looking at the stacked bar plot, that variable does not look too exciting. The violin plot would give me a maybe more refined picture, how there might be an interaction with the variable alone. And when considered together with loan, this reason might provide some useful information. But I couldn't identify that by only looking at the stacked bar plot. Here, with these more sophisticated types of analysis, I can identify interactions, or at least I can collect some hints for interactions, as you see. And I do the same for reason. Well, we don't have the time to discuss these plots in detail. It's just me liking to look at them. We also do that for the other numeric variables. Maybe one more look at the code. Again, I'm basically doing it for all my numeric columns. Creating these violin plots for reason. And there is a different way to do that. Especially if I want to create many of them. This is a bit easier to look at, probably. The issue is that, well, advantage, disadvantages above. I had more information on the, or I had the information of the distribution for, well, that's the year at present address across credit reasons for goods and bad. Here I had the lines highlighting characteristic points, and in the below example, we have a little box plot in the middle. So you decide for yourself which one you like better and find more useful. Okay, done. Well, some maybe even more exotic, no, not more exotic. Of course, you can't only, the histogram is not all you can do. You can also do a density plot where you have this kernel density estimate also on top of your histogram. That's nice. Or you can do that for pairwise, for pairs of variables. Look at that one, pretty cool. Again, you have the distribution of an individual variable. I have client age, and I have the CLNO, where was the number of credit lines. Yeah, so sort of makes sense. We saw earlier in the correlation matrix that these variables are pretty correlated. So we might want to analyze what's their joint distribution. How does that look like? And that would be a nice way to do that. We have the individual distribution, also we have this joint distribution. So that's a nice plot, doing this joint plot here of multiple variables with a kernel density estimate. Scatter plots are also a way to examine multiple variables at once, and we can color code them. so that we see essentially 3 dimensions in one picture, also trying to detect some patterns that indicate three-way interactions. Obviously, three-way interactions are hard to spot visually, but that could be here. Or last one, more exotic one. The most exotic one I left for last, swarm plot. Maybe if you like that stuff, have a look at the Seaborn documentation, what else is in there. Oh, it's a bit slow. Maybe I should switch to the pre-computed version. Ah, no, here we go. That looks fancy, doesn't it? We have good and bad, and we look at the variable value and how that distributes. And it's quite an interesting result that we have these very astonishing, if you wish, occurrences of some values here. But well, anyways, we don't want to go into too much detail here for the graphs. I just wanted to show you a few graphs and how easy it is to create them. And this also serves as a little type of recipe. You can always, when needed, come back to this tutorial and pull out the code to create one of these graphs. That's more the idea. And as far as the function that you need to learn are concerned, they came in the first part of the tutorial, right? Value counts, the indexing, select D types, info, describe, head. These are the type of functions that you must know by heart, because Pandas we will use a lot, very much. Okay, so that was it for today. I hope you enjoyed this journey through the space of Pandas. Obviously, much more available on the web. And in the next tutorial, we will have a look at vanilla machine learning and revisit some of the stuff we did in bats, random forest, gradient boosting, all these known algorithms you will see, and you will basically see how to use them in Python. So till then, I wish you all the best, take care, and look forward to see you soon. Bye for now.